So it's a great pleasure to introduce Andrew Harder from Lehigh, who is going to continue Tony's talk. Andrew?
Okay. Thank you very much, Ludmil. Thanks for both the invitation and for the nice introduction. Yeah, so what I'm going to do is continue sort of in the same direction that Tony was sort of going in. I'm going to do a bit of recap, sort of just to go over some of the stuff that he's already said in case anyone missed his talk. After that, there's going to be a fair bit of sort of new stuff. I'll talk about some results and computations that I've done with Ludmil and Victor Przyjalkowski, and then I'll talk about some of the stuff that has been in progress with Ludmil and Tony over the last little while. So the last part of the talk is going to be fairly, a little bit wishy-washy, largely because it's mostly stuff that we've only been thinking about in the last very short amount of time. But anyway, so let's just get started, and let's start by talking about the statement of the conjecture. So this is something that Tony went over a little bit, but I'll go over it again. So the basic setup is the following. So I'm going to start with a smooth projective variety. So this is my X here, and a simple number of crossings anti-canonical divisor. So that's going to be my X and Y. This is also going to be a reduced anti-canonical divisor. So in this situation, the complement of Y in X, which I'll call U, is a non-compact Calabi-Yau variety. So I can perform mirror symmetry. I can do mirror symmetry in this context. And the mirror of U is going to be what I'll call U check. And this should be another non-compact Calabi-Yau. So in this case, this is not necessarily a variety. It's in general just a manifold, complex manifold. I'll mention below that for us, at least, we're going to sort of assume that this has an algebraic structure. I think a lot of the stuff that I'll talk about can be expressed in the context where where it's not quasi-projective, but for the simplicity, we'll stick with the quasi-projective assumption for now. Okay, so the idea is to describe how filtrations on the cohomology of U and U check are related to one another under mirror symmetry. So the filtrations that I'm interested in are, first of all, the Hodge filtration, the degree filtration. And so these are the two filtrations which appear when you think about the standard Hodge number relationship between mirror compact Calabi-Yau varieties. When I say that HPQ of a compact Calabi-Yau is equal to HD minus PQ of the mirror dual Calabi-Yau, what I'm really doing is I'm relating the Hodge filtration on one to the degree filtration on the other. So these are going to be filtrations that I'm more or less suppressing today. And what I want to really focus on is the weight and perverse Leray filtrations on their cohomology. Okay, so right, so these are the filtrations that really play a bigger role in what I'm going to discuss today. You can sort of layer on top of that the degree and Hodge filtrations, but for now, I'm going to sort of ignore them a little bit. Right, so as I said also, we're going to assume that U check is quasi-projective. This gives us a nice way to define the perverse Leray filtration on its cohomology in a canonical way. Okay, so again, continuing to recap stuff that Tony has already said, the basic expectation for these mirror pairs is the following. So I'll take what's essentially sort of the Hochschild homology of U. So this I'm going to define to be this group here. So this is the direct sum of HQ of, now, if this were a compact variety, if X were compact, I would not put the log here. But since I'm looking at the cohomology of the complement, I take log forms with log poles along the SNC divisor Y. So this is HQ omega P X log Y. So I'm going to take this direct sum. And mirror symmetry tells me that this should be related to the D minus jth cohomology group of U check. And I hope I got the indices right here. So morally speaking, this should be some relationship between different cohomology groups that will come from homological mirror symmetry. So this is what I should be thinking of as maybe being the B side. And this should be something like the A side. So stating homological mirror symmetry correctly for this should give me some category whose Hochschild homology is equal to this HHJU, and I should have a dual Fukaya style category whose Hochschild homology is the cohomology of the dual variety, of the mirror variety. Right, so I'm not going to get into the details of this, but morally speaking, this should be some isomorphism that comes from homological mirror symmetry. What I want to do now is to layer on top of this various filtrations that should be identified by mirror symmetry as well. Okay, so as I said, for compact Calabi-Yau varieties, we expect that that a similar relationship holds. But in the compact case, so maybe you should think about this as the case where Y is empty. There aren't going to be either a weight or perverse Leray filtrations, and you'll see that in the construction of the filtrations below. Okay, so first I'll describe a version of Deligne's weight filtration on the cohomology on the B side. So for this, I'll use again various pieces of notation. So yi is going to be the set of points inside of y whose multiplicity is greater than or equal to y. I'm going to take yi circle to be the complement of yi plus 1 inside of yi. So this is the points inside of the boundary divisor y whose multiplicity is exactly I. And I'm going to let yi bar be the normalization of yi. Okay, so the picture here is sort of the following. We have a collection of, maybe this is the normalization picture. So we have our boundary divisor, which looks in the dimension 2 case, something like this. So a union of lines meeting in points. So yi, or in this case, y1 will be the union of everything. Y0 will just, or sorry, y2 will be the points of intersection between these two things. The complement, so yi circle will be the complement of the intersection points in the divisor, and yi bar will be the normalization. So this will be these lines taken separately. So the boundary yi bar is the image of the points in yi plus 1 inside of yi bar, so the normalization. So in this example, it's just a collection of points that come from the pre-images of the intersection points under the normalization. Okay, so this is the setup necessary to define the weight filtration. And what I'll do is I can, from this, define residue maps. So jth residue maps going from the complex of forms on X, homomorphic forms on X with log poles on Y, to the complex. So this is now a complex supported on the entire normalization. This is a complex of degree dot minus I form, so I drop degree when I take residue, on yi bar with log poles along the boundary. Right. So I have this residue map, and I can define the weight filtration to be the kernel of this residue map. So this is not precisely the standard definition, not the precise definition, but this is analogous, or this is equivalent to the standard definition of weight filtration. You can check this fairly easily. Okay, so this is the definition of my weight filtration on the complex. I can then define a weight filtration on the on each of the individual Hodge groups by just taking the sort of the same the kernel of the same residue map. Right, so I take this kernel. I'll then, as Tony did, I'll define the weight filtration on each of these HQP groups. So these groups here, so this is the Qth cohomology, the sheaf of P forms with log poles on Y, as the image of this induced weight filtration inside of the corresponding cohomology group. So the tilde here, as Tony mentioned, is included to denote the fact that this isn't the standard weight filtration as you would define it usually using mixed Hodge theory. In general, what you do is you'd shift this I if you were defining it this way. But for us, this is a more convenient piece of way to write the filtration. So we'll do it this way. Okay, so once I have my filtration on each of these Hodge groups, I can define an extended filtration on what I've denoted as the this Hochschild homology group here. And this will give me a filtration on this entire by just taking the direct sum of all the weight filtered pieces. Okay, so that gives me a good description of the weight filtration on Hochschild homology. Once I have that, I can try to figure out what this is related to under mirror symmetry. And this should be related to the perverse Leray filtration. Right, so for any variety and a map of varieties from V to W, maybe there's no there exists here, and map between these varieties, I can build what's called the perverse Leray filtration on the cohomology of the original variety by taking the perverse truncations of the push forward sheaf, so the derived push forward of the coefficient sheaf. And so this will give me a filtration on the derived push forward. And I can use that to build a filtration on cohomology just by extending it in sort of the same way that I did before. Right, so this gives me a canonical filtration on the cohomology of V with respect to a map, which doesn't depend on any choices except for the map itself. So the sort of very nice theorem and very helpful theorem of Di Cataldo-Migliorini tells me that if I have an affine variety, then this perverse Leray filtration, and maybe I also need that this map is proper. Maybe I'll also assume that. Then I get a nice relationship between the perverse Leray filtration and the flag filtration with respect to the same map. Right, so this makes the filtration very computable. So this means that if I embed W inside of some affine space, and I build a linear flag inside of that affine space, I can compute the perverse filtration by taking restrictions to the pre-images of each of these linear subspaces. Right, so here's the filtration that I want to define. So this is maybe I should point out, that this is just a shift of the perverse Leray filtration. And I think I maybe got the index wrong here, but it's not a big deal. So this is the shift of the perverse Leray filtration, and it can be computed just by restricting cohomology groups to the cohomology groups of the pre-images of these linear sections. Okay, so this is the general setup, starting with a variety and a map. More generally, or less generally, I suppose, if I'm given a variety, I can give you sort of a canonical map to its affinization. Right? So there's this affinization map, which goes from each V to the spectrum of its ring of functions. So from here on, what I'll be interested in is this map. So I'll be looking at the perverse Leray filtration of the affinization map. So this is something that's canonically associated to a variety. I'll also assume that this is going to be a proper map. So this is something that's proper over its affinization. And therefore, I can compute the perverse Leray filtration just by this flag filtration. So this is a well-defined and canonical object associated to my variety. Okay, so as we saw earlier, the mirror P equals W conjecture then says the following thing. So if I take two log Calabi-Yau varieties, U and U check, I guess, then mirror symmetry should identify the perverse Leray filtration or the shifted perverse Leray filtration on U check with the shifted weight filtration on U for all I and J. Right? So the idea is that homological mirror symmetry should identify the cohomology groups without the filtrations. And sort of the new input here is that these filtrations should agree. Okay. So that's my reiteration of this conjecture. And so I'll make a couple of remarks before moving on. So I've spoken about this, over the last couple of years, and the way this conjecture has been stated has evolved a fair bit. So it was originally stated on a very numerical level, relating various, E polynomials in some sort of contorted way. So this, the way that was stated is still valid, but I think this is a much more, elegant way of writing this down as some sort of identification between actual filtrations. And this is an identification which should actually, match cohomology groups, not just dimensions of groups. So that's sort of one thing that I'd like to highlight about the way this is written. I should also point out, and this is something that I've mentioned a little bit already, is that the filtrations, the P and the W filtrations, these are canonical filtrations associated to the varieties. So these are things that don't depend on data that I choose, just sort of the algebraic structure. So once I have the structure on both sides as an algebraic variety, I get these filtrations for free.
So if you think of it in terms of categories, as you mentioned. On the right-hand side, it's clear it's a Hochschild homology of some category like whatever DB. But on the left-hand side,
Actually, it's not clear on the right-hand side either.
I mean, there should be some category, like derived category of coherence shifts on the U or its cousin, and on the left-hand side, it's less clear.
On the
I mean, at least it's written like non-symmetrically. HH on the right-hand side.
Oh, so my claim is that this should be like a Hochschild homology of a Fukaya style category. Is that answering the question?
Yeah, I mean, I would prefer that.
oh, right. So you'd prefer that I wrote it?
Yeah,
as
because
like,
then it's clear mirror symmetric statement. Yeah.
Yeah, that's true. So maybe it'd be better. I mean, I think maybe the best description of how this is written down is maybe more in terms of like compactly supported objects on things, if you want to see it coming from categories. But yeah, I mean, I am sort of implicitly identifying this with like a Hochschild homology of some sort of Fukaya category. This is true.
Something.
Go ahead, Dimo.
Yeah. No, it's just a stupid question. I mean, you sort of implicitly assume that this U or U hat is convex, meaning like projective or affine. Is it in any way automatic or?
No, I think it should be an assumption.
Yeah. Yeah. I mean, I should be making assumptions about the structure of these things.
But is there any reason to think it should be preserved by mirror symmetry or something? I mean, it's a special type of variety in some sense.
Yeah, not very special. I think it's it's kind of proper over affine. It's
all right. Yeah.
Yeah.
I mean, you can't like remove a point or something that destroys it completely right away.
Yes. But proper affine, it's more or less the natural class when you can have boundness for some convexity infinity.
Okay.
Yeah, I mean, these assumptions that you're talking about, these are things that are sort of naturally satisfied in the examples that I've looked at. So I'm comfortable making this assumption.
Can I, since there was an interruption, can I ask a couple more questions?
Sure.
So when, first of all, you mentioned some hypothetical derived category whose Hochschild homology would be this HHJ of U. Some coherent sheaves category, but we do not know of the existence of or the construction of such a category. Am I right?
I personally don't really know such a thing. No, I think if I would assume people who know more about homological mirror symmetry than I do could cook something up, but I don't know anything.
No. I suspect that this would imply if we knew such a category existed, it would imply, for example, Kawamata's D implies K, whatever conjecture, for example. But the other question I was asking is, when you say the filtrations are canonical, you mean that, for example, if I realize the same U in different ways as complements of anti-canonical divisors on different varieties, I get the same filtrations on this open set?
Yes, that should be true. I mean, the weight filtration is canonical, and the perverse Leray filtration is just some filtration obtained from, the perverse truncation and blah, blah, blah. It's a canonical thing obtained from the affinization map.
Yeah,
so
but
that's,
in fact, there is an interesting question. If you treat you check as a just non-compact symplectic variety, yeah? Is it filtration? Is it filtration canonically associated just to the structures non-compact symplectic variety?
Yeah, that sounds like a I mean, that's a good question.
Yeah.
I certainly don't know the answer to it.
If it's HH of some Fukaya category, probably it is. Yeah, because it should depend on the symplectic structure, provided you have complete convexity at infinity.
Okay. I mean, I'll talk about how this can be sort of seen in terms of the torus fibrations in a little while. So maybe that'll say something towards that. It won't answer any of the questions, but I'll say something.
Just a second.
Yeah.
May I have intuition that perverse called filtration on the left-hand side, it will be kind of closed submanifold, which goes to infinity in pieces of kind of bounded dimension in something like this. Yeah, like completely supported patterns. And so, for example, image of completely supported cohomology in whole cohomology is a part of this perverse filtration or not?
So you're asking me if you can realize parts.
Pure geometrically, yeah. Because there is natural subspace, for example, image of completely support.
In the weight filtration.
Yeah.
No,
in perverse. I mean.
I'm not sure. I mean, this is something I should think about, but I don't know the answer. Yeah, sorry. So I guess I'll say a little bit more about these statements here. So these are essentially canonical filtrations coming from algebraic structure. One nice consequence of this conjecture is that it says that if I start with an affine variety, then the mirror should have Hodge-Tate cohomology. So this is some simplicity condition on the structure of the mixed Hodge structure of the cohomology in U. So this is sort of, relating affineness to cohomological or mixed Hodge theoretic structures. So this is sort of a nice consequence. And I should also mention that, for me at least, the natural way to start thinking about this comes from conjectures of Katzarkov-Pantev and Pantev, which are conjectures about how the cohomology of Landau-Ginzburg models and Fano varieties are related to one another under mirror symmetry. Okay, great. So this is my background discussion. I'll talk a little bit about some examples as Tony promised I would in some of these in some cases. So these are just examples that I've sort of gone through and computed. I mean, nothing is very deep. It's just more or less just verifying that the basic ideas behind these conjectures are really things that make sense. Okay, so the first set of examples comes from del Pezzo surfaces. So I'll let xn be a del Pezzo surface of degree n, and I'll let y be a smooth elliptic curve inside of this del Pezzo surface. So this forms a log Calabi-Yau pair, and its mirror can be constructed fairly easily. So you take a rational elliptic surface. So if I have a rational elliptic surface, I have a map to P1, and I assume that this rational elliptic surface has an IN type fiber over infinity. So that was this thing that I erased, which is, it's just a cycle of n curves as the fiber over infinity. And I'll let dn be this fiber. So the mirror pair then consists of Zn and Dn. So the complement of this is a log Calabi-Yau variety. So this is the mirror pair. So I have X, N, and Y, Zn, and Dn. Okay, so in both of these cases, we can look at, I mean, just as a first approximation to why this conjecture should be true, I can look at the depth of the weight and the perverse Leray filtrations in these cases. So the affinization of the complement of a smooth elliptic curve inside of xn is of course the identity because it's an affine variety. And the affinization map of the mirror variety of this Zn minus Dn, this is just the restriction of this map from Zn to P1 to the complement of the fiber over infinity. So this is going to be a map to a one-dimensional space and a map to a two-dimensional space. So just, looking at the different flags that determine the perverse Leray filtration in these cases, you can see that the flag determining the perverse Leray filtration on xn minus y is, well, you can take the restriction, the pullback to an n-punctured elliptic curve sitting inside of this complement of a smooth elliptic curve. And you can take then the deeper part is just a collection of points. And on the other side, so this is a filtration of length 2, right? So there's 2 pieces in the filtration. And then the filtration on the other side is of length 1, or there are 2 sorry, there are 3 non-trivial graded pieces in that filtration. Sorry, yeah, possibly non-trivial. And then on the other hand, we have 2 non-trivial possible graded pieces in the filtration on Zn minus Dn. Okay, so we have these lengths of the length 1 and length 2 filtrations. Maybe I should have said 2 and 3. And then on the other side, we can look at the length of the weight filtrations on the corresponding objects. So the weight filtration on Hochschild homology of xn minus y, this is length 1 because what I'm doing is removing just a smooth divisor. So this is determined by a single residue map. And the weight filtration on the cohomology of the complement of dn in Zn is going to have length 2 because it's going to be determined by 2 residue maps. So you see, just like at this very coarse level, that the length of the weight filtrations agrees with the corresponding length of the perverse Leray filtration. And you also notice that in this case, I'm not treating this as an asymmetric thing. I'm treating both of these things as living on the A side and the B side, not at the same time, but in alternating fashion. So the small computation that you can do, and it's not very hard, is that this mirror P equals W conjecture holds numerically for smooth anticanonical pairs and del Pezzo surfaces. So for the pairs that I mentioned before, you can check that this is all true. Okay, right, so this is a relatively easy, straightforward computation. You can extend it to pairs consisting of a smooth del Pezzo surface and a nodal anticanonical divisor. This is a totally fine thing to do. You can do this computation. It's just sort of just more busy work. A slightly more interesting computation is maybe how this all works in higher dimensions. So we've got several examples that we know how to compute in higher dimensions as well. And these come in the following way. So let's start with the example of toric threefolds. So I'll take a reflexive polytope in dimension 3, and I'll take x delta to be a crepant resolution of the associated toric variety. Okay, so in dimension 3, these toric the toric variety associated to a reflexive polytope is this is Gorenstein Fano if I don't resolve, but in dimension 3 I can actually get a crepant resolution, which gives me a weak Fano variety. I can take a smooth anticanonical K3 surface in this thing, and then the corresponding pair x delta s delta is log Calabi-Yau. I can construct its mirror in a fairly explicit way in this case. So what I do is I can take the polar polytope, and I can take the corresponding resolution of the toric variety associated to that polytope. So this is the same thing with a different polytope. And then I can build the log Calabi-Yau pair by essentially by blowups instead of smoothing, essentially in this case. So I'll let d delta circle be the toric boundary of this toric variety, and I'll let s delta circle be a smooth anticanonical divisor. And then I can build this U delta circle by taking sequential blowups of the components of the intersection of S delta circle and D delta circle. Right, so I blow these things up sequentially. This will give me some variety which maps onto P1 because I'm basically blowing up the base locus of a pencil. Then I can take the proper transform I can remove the proper transform of the boundary divisor, sort of the same way I did in the previous case, to get some variety which maps to A1. So it's proper over A1 in this case. So this is my mirror construction. And I mean, just maybe in a little bit more of an abstract way, how should I think about this? Well, I have 2 toric pairs consisting of my toric variety and its toric boundary. So these are in some sense mirror log Calabi-Yau pairs. And the smoothing of d delta to s delta, so going from the very degenerate boundary divisor to a non-degenerate boundary divisor, should be equivalent to the process of blowing up the intersection here on this side. So you can modify this mirror construction to say, if I only want to partially smooth my toric boundary divisor, I can only partially blow up the base locus of this pencil, and this will sort of in the same way give me mirror pairs that look fairly similar. But in this case, the mirror won't be projective over A1; it'll be projective over some higher dimensional base. Okay, so just to give a very simple example, if I start with this polytope here, then the corresponding toric variety is just a resolution of this very singular quartic. The dual toric variety is then going to be essentially, or the dual polytope is the polytope determining P3. So it's just the standard sort of simplex. And the corresponding mirror dual is the blow-up of P3 in a bunch of quartic curves intersecting coordinate hyperplanes. So I take a quartic hypersurface inside of P3, I intersect with the boundary divisors, and I sequentially blow up the corresponding curves. And then I remove the proper transform of the boundary, and I get the mirror dual. Okay, so the thing that you can prove in this case, which is, I mean, it's significantly more difficult than the previous case, but it's still sort of just a direct computation, is that for any reflexive polytope in dimension 3, if I build these perspective mirrors, this isn't going to be mirror in any sense except for the sense that I'm talking about, then these two pairs satisfy the mirror P equals W conjecture numerically. So you can just check this in this sort of straightforward case. Okay, so one interesting point about this collection of examples is that it doesn't start with a Fano. It starts with things that are not quite Fano. You can also extend these computations to the partial smoothing, partial resolution situation that I was talking about earlier. So instead of completely smoothing the toric boundary, you can smooth instead to like a degenerate hypersurface. So say like in P3, this is like smoothing the union of hyperplanes into a pair of quadrics or something like that. You can do the same construction. You can get the same type of relationship there. Okay, so other cases where this can be computed is for Fano threefolds themselves. So Victor Przyjalkowski has constructed prospective mirror duals to all Fano threefolds. The construction is fairly similar. What you end up doing is you take a toric variety and you take a very special pencil of hypersurfaces in that toric variety. You blow up the base locus, and then you remove the proper transform of the toric boundary. The way one chooses these polynomials is a bit of an art. It's a bit ad hoc. But he's been able to construct things that are very well supported to be mirror dual to each Fano threefold. So you can check in those cases. So for any Fano threefold, consists with a smooth anti-canonical divisor, you can build a thing using Victor's method here, which is expected to be mirror to that Fano threefold, and you can verify that the mirror P equals W conjecture holds numerically in those cases as well. So you get some sort of interesting phenomena coming up here. I should also mention that in both of these theorems, this one here and this one here, the result is treating both the proper over A1 variety and the complement of the anti-canonical divisor. You can treat these both as being on either side of the mirror and verifying this conjecture that I made. So like it's somewhat robust in that I'm not just always starting with the Fano and going to something that's proper over A1. I'm doing something a bit more subtle than that. I can go back and forth. Okay, so I should make a remark here that, I mean, this is where this all sort of started for me personally, is that, you do these computations and you can see that what we were doing when we were doing these computations is essentially we were checking these conjectures of Katzarkov-Pantev and Pantev in various cases. So these conjectures say things like, if I have a Fano variety, I can take its Landau-Ginzburg mirror and I can relate cohomological invariance of the Fano variety or what have you to the Hodge theoretic invariance of the Landau-Ginzburg model. And if you start doing these computations, you sort of see that the way you have to compute on both sides is essentially relating, bits and pieces, and the way these bits and pieces glue together sort of is essentially this near P equals W conjecture. There's close relationships between these two different classes of conjectures. So this was, for me, where this all started. And so in some sense, you should really be thinking about this if you know about these KKP conjectures as sort of a refinement of those conjectures to sort of non-compact varieties and things like that. Okay, so so everything that I've said up until now is quite old. This was stuff that these are computations that were done in like 2018, and as I already mentioned, these are results that are done by essentially direct computations. There's no real subtlety involved. It's low dimensional. So the goal would be to basically to understand how this whole conjecture on all this stuff interacts with various forms of mirror symmetry, and to use what we can learn by doing this to build tools to prove it more generally. Right. So this is the idea. I mean, I think as Tony mentioned, Sukju, one of his students, has done various bits of work that tell us how to relate this conjecture to homological mirror symmetry and how it relates to like a relative version of homological mirror symmetry in the one or two potential case. So I'm not going to say much about that, but what I want to do is I want to talk about how this conjecture can be discussed in terms of torus fibrations. So Tony did mention this a little bit in his talk, but I want to go into a bit more detail. So let's start by assuming that U and U check admit dual torus fibrations. So what I mean by this is that there are torus fibrations from U and U check to a base B. And so I'll call these pi check and pi. And so our goal is to use the geometry of these fibrations to give a geometric version of this P equals W conjecture. Okay, so I'll introduce a bit of notation. It's, I mean, I guess generally a bit more than I like to use in talks, but I think it's necessary for all that we want to talk about. So I'll let B0 be the smooth locus of pi, and in fact, this will be the smooth locus of pi check as well. Then J will be the embedding of B0 into B. I'll use pi 0 to denote the restriction of pi to the pre-image of B0. So this is the restriction to the collection of all smooth fibers, and pi 0 check to denote the corresponding restriction to the collection of smooth fibers of B of U check. Then I'll also assume that pi and pi 0 are Q-simple torus fibrations. So this means that essentially I can deduce anything about the derived push-forward cohomology sheaves, these Ri pi's, from taking the Ri pi 0 and Ri pi check zeros and pushing forward from the smooth locus to the singular locus. So from
May I ask, I'm a bit confused because I'm thinking in terms of original P equal W where it's Hitchin system, yeah? Like, and then if you ignore the discriminant, basically you throw away the most interesting part because then you have just cohomology filtration on the cohomology of abelian varieties, which is kind of stupid. So then I'm confused why you throw away.
No, but here we get interesting direct images. Yes. It's...
What do you mean? It's just cohomology in the case of Hitchin system, and I'm just looking at this example, like U, for example. Then what you get is just a variation of, you have just a constant cohomology of abelian variety.
Yes, sure, yeah, but this direct image, because the topology is kind of complicated, it's complement discriminant. You get some kind of bizarre things in this.
Yeah, I mean, generally speaking, in these types of cases, you can sort of assume that if you're not worried about actually special Lagrangian torus fibrations, you can usually get away with deforming things out so that they're quite simple in this way. And this just gives me a closer connection between the torus fibration, the cohomology of the direct images of the torus fibration, and the Hodge numbers. So, I mean, so this is an interesting question because what I'm sort of getting at here is some like very floppy analog of the P equals W conjecture. So the P equals W conjecture would be talking about, dual special Lagrangian torus fibrations on Betty moduli spaces here. And in that case, if I wanted to do the same thing, I really wouldn't, do this. I would not do that at all. I would, instead of this, I would take the perverse Leray filtration and try to relate the graded pieces of that. And so I wouldn't be throwing things away. But in this case, since I'm just really worried about topological torus fibrations, I'm gonna forget about the singular fibers. Maybe this is sort of a first approximation at what one should really be doing here, though. Hopefully that's somewhat meaningful. Yeah, any other questions at this point? Okay, so I'll make this assumption that I have these very simple types of dual torus fibrations on each side. And what this will mean is that basically I'm going to ignore anything happening at singular fibers and just treat this as if I was dealing with torus bundles.
Oh, now maybe I have a question. In kind of Gross-Zieberg picture, the originally started with some kind of very simple types of singular ramification divisors. Is it in this case your property satisfies?
Yeah, exactly.
Yeah,
so these are the types of singularities that I'm thinking of. So I forget exactly. So the positive and negative vertex, I think, is what they're called in the three-dimensional case. So those are the types of things that I'm interested in here. This might restrict the the collection of varieties that this applies to. I don't think it's that bad. I mean, at least in terms of like toric complete intersections, this should be good enough. If you're just worried about.
Basically, let me again, because I'm still confused. So you have just basically the local system on the with the action of the monodromy, but on sort of a maybe complicated manifold, like the variety minus the discriminant. Yeah.
Yeah, exactly. So basically, I'm trading. Instead of the way maybe you could think about it is like if you take the Hitchin system, and instead of like requiring that it be special Lagrangian, what I could do is I might be able to like deform this out. So instead of a very simple discriminant locus and complicated sheaves on the discriminant locus, I have a much more complicated discriminant locus and simpler sheaves. So if you think about it in like the two-dimensional case, instead of having like these dn or an type singularities, I can sort of deform an elliptic fibration so that these singularities all morsify. So what I'm thinking about is sort of the most floppy version of this.
Okay, thank you.
Right. Okay. So if I have this structure, I can then think about the Hodge theoretic duality as being recovered from these sheaves, or coming from these sheaves. So as Tony mentioned, this duality of torus fibrations means that I get an isomorphism between Ri pi 0 z and Rd minus I pi 0 check of z for all I. And furthermore, I can use these sheaves to reconstruct the open part or the smooth part of each of the torus fibrations. Right? So I just take the quotient of the R push forward sheaves, sort of the top part, and I quotient by the Z part. And I can do the same for the dual fibration, and I can I can recover my my fibration from this. So really everything involved in these torus fibrations, at least cohomologically, is determined by the affine structure in this case. That's essentially what I'm saying. I'm restricting myself to a very simple situation, and in which essentially what I'm doing is relating dual pairs of affine structures on B0. Okay, so what one expects in this situation is, in analogy with the compact case, is that the Hodge groups are isomorphic or equal to the affine Hodge groups. So this is this is an expectation, and you'll see in a second that this is actually sort of a very helpful expectation, because we get nice dual filtrations coming from on these groups, coming from perverse and weight type things. So this is a good sort of combinatorial, at least, model of what we proposed at the beginning. So the goal now is to build filtrations on these affine Hodge groups, which imitate the perverse and Leray filtrations and weight filtrations. So in fact, what I'm going to do is I'm going to build something that imitates the weight filtration, then look at where it goes under duality, and see that that looks a lot like something that we constructed. It looks a lot like a perverse Leray type filtration. It's some sort of geometric filtration based on restricting to not submanifolds, but subspaces, sub-torus bundles. Okay, so in order to construct the weight filtration on these affine Hodge groups here, what I need to do is I need to make some assumptions about how the Lagrangian or topological torus fibrations that I'm presuming exist behave with respect to the compactification. So I'm going to assume that this map pi extends to a map pi bar from X to a compactification of B. So here B bar is going to be a manifold with corners, and I'm going to describe the stratification as follows. So I have B bar, and then I have the strata in my corner structure described like this. So in analogy with what I talked about before in the boundary divisor, I'm going to let dBi be the complement of the I+1 part of this corner structure in dBi. And I'm going to use this ui to denote the inclusion of dBi inside of B bar. Okay, so my assumption here, so I'm assuming that it extends. I'm setting up notation here. And then I'm also assuming that when I restrict pi to each of the sort of open pieces of the strata of the boundary divisor, this gives me a z-simple torus fibration for all I. So just that this behaves nicely. Okay, let's see. So, I mean, this is a pretty reasonable thing to expect if you're just worried about torus fibrations. You know, this is what you get if you look at the moment map from a toric variety to its moment polytope. So generally speaking, this is not a crazy assumption. So once I have that, I can essentially build a weight filtration on the affine Hodge groups in the following way. So I can take the residue map. So I gave the residue map, I didn't really explain what it was, but really the way you generally define it is in terms of differential forms, but you can also define it purely in terms of sheaves in sort of, not the following way, but it gives you the following data. So if you have the embedding of U into X, and I push forward some coefficient sheaf on U, I get a map from that to the push forward from yi circle into X of the corresponding coefficient sheaves on the pieces in the boundary divisor, so shifted by I. So I can push this down along the map pi. So that'll give me the map pi here and the map pi I here. And I get corresponding maps between the coefficient sheaves in the base. So the push forward sheaves like this. And the simple proposition to prove is that this map of sheaves on B bar is going to respect essentially the Leray filtration. I mean, the Leray filtration here is obtained by taking the canonical filtration on these complexes of sheaves. So I mean, this is going to give you a nice map between the graded pieces of the Leray filtrations. So just, you know, this is a bit more complicated than what I've said, but I essentially get imitations of the residue map on push forwards of these RQ sheaves. Okay, so of course, you know, the reason that I stated the weight filtration on sheaves before as a kernel of some map is because that transfers over much more easily to this context. Right, so generally speaking, you define it as a subsheaf of the sheaf of differential forms, but this is a little bit dicier. So it's easier to transfer it this way if you write it as a kernel of a restriction of a residue map. So since I have the residue map given in terms of these RQ pi sheaves, I can now define a weight filtration in terms of these corresponding residue maps. Okay, so I have this weight filtration being the kernel of these residue maps that I construct. And then I follow exactly the same recipe as before, and I can define some wi tilde on these affine Hodge groups as the image of the embedding of the cohomology of the weight filtered sheaf, or the weight filtrans of the sheaf. Okay, so I get an induced thing that I expect to be like the weight filtration on these affine Hodge groups. So what we want to do now is we want to talk about how this can be transferred to a geometric type filtration on the dual affine Hodge groups. So this is not very hard to see. What do you do? So you can take, so you take the top level residue map. So this will go from RD minus 1 here to RD minus I minus 1 on AYI. Then you think about this dually, and this gives me an isomorphism between the R1 on U check pushed forward. So this is the R1 of a torus bundle on B bar. And then I can take the dual of this, and this will give me the push forward of the dual torus bundle associated to each yi circle. So I push this forward from the interior of each stratum of this boundary of this corner, the sort of corner structure in this manifold with corners onto its closure. So I have a dual torus bundle living over parts of this manifold with corners, and I have another torus bundle living over the manifold with corners here. This is a map in cohomology, so I can take the dual map in homology, and this will give me an embedding of the first homology sheaf of the torus bundle, of some torus bundle living on parts of the boundary, into the first homology sheaf of some torus bundle living on the closure. Since these are just torus bundles, I can sort of extend this to a map of the torus bundles themselves. I mean, going from homology to the torus bundle is bad. Question?
Oh yeah, I have a question. Yeah, you do all calculations outside of discriminant, yeah?
Yeah, exactly.
And how you argue eventually for discriminant?
Yeah, I think I haven't worked out the details, if I'm being completely honest about that. At the moment, I'm forgetting about this.
Do they exist, these details? Because I know that for Hitchin system, it's kind of, you cannot do it just by induction using the, because it's too the structure of discriminant is too complicated. So.
Yeah, I mean, so these are very simple torus fibrations that I'm working with. So this is one of the things that I'm sort of expecting to help me out here. Yeah, and so do torus fibrations like this actually exist? Yeah, I mean, if you're just worried about this on a topological level, you know, I think this is not super hard to construct. And this is one of the goals of the project. It's actually to turn this into a functional way of verifying these conjectures.
Can I also say one more objection here? So I think the last dimension when you can assume that your discriminator has a simple kind of singularity is 3. Because beyond dimension 3, I don't think you can expect you know, both your monodromy polytopes to be like unimodular simplices.
Ah, okay. So maybe this argument will only work in dimension 3, or up to dimension 3. Yeah, I mean, I'm not claiming that this is rigorous at all at this point. I mean, this is stuff that I've been
just arguments in favor.
Yeah, exactly. I think that's probably the best way to think about what I'm writing down right now. Yes. But you get these, I mean, if you just worry about the smooth part, you can, you know, just push forward, you get this torus bundle on the boundary. And what you can deduce from this is that, so we have an embedding of torus bundles living on pieces of this boundary so that the induced maps and cohomology sheaves agree with the residue map. Okay, so if these are maps coming that are dual to the residue map, so I can see that if I let yi check be the union of these torus bundles, then the weight filtration is equal to the kernel of this restriction map in the dual to some cohomology sheaves of a torus bundle in the boundary. Right, so this looks a lot like the way I constructed the Leray filtration, the perverse Leray filtration. And so the conjecture is then that if this can be done, then this is homotopic to these pieces, these hyperplane pullbacks for some specific choice of affinization map. And so I only have a couple minutes left, so I'll just sort of go through a very basic example of what this all means in a specific situation. So if I just look at the moment map for CP2, to delta, so this is some polytope, then CP2 is going to be essentially a trivial torus bundle over this polytope. And what I get by doing this process that I mentioned before is I get just tubes sitting on the boundary of this moment polytope. So I have these three tubes living on the boundary of the toric polytope, and the restriction maps to these tubes and the restriction map to the intersection points in the tubes. These give me the dual to the weight filtration. And okay, so you can just do this combinatorial process and you get these subtorus bundles. And you can actually verify that this is essentially what you would expect by doing the other process that I was talking about before, just taking the affinization of the mirror dual. So the mirror is C star squared, and you can take as your flag, you can take a thrice punctured elliptic curve. So this is something coming from canonical hyperplane section of the dual toric variety, and you can take intersections of these thrice punctured elliptic curves, and that'll give you 3 points. And that's exactly what you're seeing here. You have this union of tubes is homotopic to a thrice punctured sphere, and the 3 points that you see inside are 3 points. Okay, so that's essentially the outline of what I had to say. Just as far as outlook goes, the idea is that this sort of geometric combinatorial picture can be used to be extended to give you an actual proof of this P equals W type conjecture for toric complete intersections. I mean, I wouldn't expect to really use the topological picture that I described above, except maybe in examples. But I think applying the ideas behind that, plus maybe tropical Hodge theory and things like that, could lead to a nice proof of these types of conjectures for toric complete intersections. And maybe, so another thing that Tony talked about a little bit, which maybe I won't go into detail about, is that it'd be really interesting to understand better the relationship between the mirror P equals W conjecture and homological mirror symmetry. So this is something that his student Sukju has been working on in the two potential case. And these two things are both things that Sukju's done good work on. And the last thing that's sort of suggested by this is that there should be, or there might be, some sort of A model variation of mixed Hodge structure dual to the B model variation of Hodge structure. So in work of people like Irotani for compact Calabi-Yaus, he's looked at, you can take the B model variation of Hodge structure of the Calabi-Yau variety near a maximally potent monodromy point, and you can really match it with like a literal A model variation of Hodge structure coming from essentially the integral structure is provided by K theory, and then the complex structure is provided by quantum cohomology. So in this case, the idea is that maybe hypothetically at some point in the future one could do a similar thing, relating a B model variation of Hodge structure of log Calabi-Yau varieties near some boundary point to an A model variation of mixed Hodge structure coming from Gromov-Witten theory, and with the weight filtration provided by the affinization in the same sort of way. Okay, so that's what I had to say. Thank you.
All right, let's thank Andrew. More questions?
What's the tropical version of P equal W?
What's the tropical version of? This is, I guess that was sort of what I was trying to express near the end.
Yeah, but I mean, this probably I missed what is the P side.
Yeah, you should ask Ilya.
No. For the Hodge theory, yeah, I know something, but for the perverse filtration, I'm a bit.
I think you could still probably do it by taking appropriate hyperplane sections.
Just okay, yeah.
I think you just take appropriate tropicalizations of hypersurfaces.
All right, yeah.
Intersections of those things.
Other questions?
Can I ask a question? This might be a stupid question. This is Carlos. You probably said this, and I probably missed it, but can you just say briefly, how do you basically get the identification between the two cohomology groups on the two sides?
Right. So yeah, this was something that was discussed. So hypothetically, this should arise from homological mirror symmetry, identifying Hochschild homology of some sort of derived category and some sort of mirror dual Fukaya category.
But in the examples, I mean.
Oh, where the examples that I worked out. Yeah, so that's just matching numbers. So these are just numerical calculations. So I compute dimensions of various weight graded pieces.
But do you have some ideas to how in the examples you would actually get the sort of the right, I mean, the equality of the filtration should, for example, guide you to get which is the identification. But do you have some idea in the examples how to define the isomorphism?
Examples. So say for del Pezzo surfaces, yeah, I think in these, say the del Pezzo examples, I think it's probably something that could be worked out. Maybe by, enhancing some sort of compactly supported version of HMS between the del Pezzo surface and minus the anti-canonical and its and its mirror. I mean, you can also sort of think about this. You can sort of do a cheap version of this maybe, and you can take, you have functors between the Fukaya-Seidel category of the Landau-Ginzburg model and its smooth fiber. So if you enhance that to a map in Hochschild homology, maybe you can extend this to a long exact sequence in cohomology, and so the thing sitting at the other part gets identified with the cohomology of the complement or something like this.
Mm-hmm. I mean, you might get something that looks a little bit like a map, or at least up to an exact sequence or something, and then the conjecture would be that it's an isomorphism.
Yeah.
Okay, thanks.
Other questions?
Can I ask a question which goes one step beyond the last case you considered with just a toric? What happens in the case of a pair of pens when you have like Pn minus, your Y is a pair of pens, so you have Pn minus n plus 2 hyperplanes. So what does this P equals W say?
So this isn't log Calabi-Yau, right? So I'm not sure exactly what it says.
Oh, I see. So you want, I see. Okay. All right. Thanks.
That would be, I'm sure there's some.
Oh, I see. Okay.
Well, if there are no other questions, let's thank Andrew again. And we'll resume in 25 minutes with a talk by Matt Ball.